So in class we did some work with the forces that are involved in this simple harmonic motion, this tub going up and down because it's attached to a spring. We saw that there's this interplay between the spring force, which is largest when the spring is most stretched out, and small when the spring is not very stretched out, and gravity, which is constant. So those two together give us this overall force that always pulls the spring, or pulls the tub, back toward its resting position. So here's the resting position. If I displace it upward, it goes back toward that position. If I come back to the beginning here, if we displace it downward, that force pulls it back toward the equilibrium position. But it doesn't stop there because, well, it has inertia. So it continues moving past that equilibrium position. Now, the motion of this thing is interesting as well. Specifically, let's talk now about the position, the velocity, and the acceleration of this tub at each moment in time as it goes up and down. We'll utilize this diagram again. I've condensed it a little bit and eliminated the middle steps along the way. So we're just going to look at kind of the extremes and then the absolute middles here when our mass is at equilibrium. And we'll analyze this in terms of position, velocity, and acceleration. Just get an idea for when each of those quantities is its largest, when it's its smallest, when it's zero, things like that. So position's a pretty easy one to start with. Position, we'll just say, is the distance away from the equilibrium spot. And so we also could talk about whether it's above or below equilibrium. So this one's pretty clear. We have a maximum position above equilibrium here at T0 and again at T4. So we'll just call that max upward displacement. Here's our max downward displacement, upward displacement again. The farthest downward displacement happens right here when it's at its bottom point. So that'd be our max downward. And then at these spots, we're looking at distance from equilibrium. Those are at equilibrium, so those will just be zeros. Now let's consider velocity. So at each one of these points where it gets to its high point or a low point, our mass starts out going upward toward that high point. Once it gets to the high point, it's going to start going downward. So it was moving up, it's going to move down. In between those 2 points, it has to stop for just an instant. So every time we have a maximum or a maximum upward displacement or a maximum downward displacement, at that same moment we get to our zero velocity. That tub stops and changes direction at that point. Now, going from T0 to T2 here, we can see that our tub is moving downward. It's going to end up getting to its fastest speed right here at T1 and again at T3. If we want to include direction, then we'll have a maximum downward velocity here and a maximum upward velocity here. Now, that may not be obvious that it would be those points. We'll come back to those after we talk about acceleration, though, and that will make this a little clearer. So for acceleration, we're going to consider the forces that are acting, because we know that force is equal to mass times acceleration, or rather net force is equal to mass times acceleration. So if we can figure out what's the net force at each moment in time, then we can just say, okay, well, that's proportional to acceleration. So when we have the biggest net force, we'll also have the biggest acceleration. So we did this in class. We said that at this moment where the tub is as high as it can get, it has the maximum downward force that it's ever going to have. So just a little tiny upward force from the spring and that same downward force from gravity, that's where our difference between gravity and the spring force are going to be at their greatest. So we have a maximum downward force at this point right here, which means we're going to have a maximum downward acceleration at that point as well. And that'll be true again when it gets up to the top. And then for the very bottom point, this is where the spring is as stretched out as it can get. So that upward force caused by the spring, that's as large as it can be. And it's going to be larger than the force of gravity at that point. That's the biggest difference we can have. So we'll have our biggest net force in the upward direction here in the middle, which means we're also going to have our maximum upward acceleration at that point. And then last up is these 2 points here. Those are at this dotted line that we call equilibrium. It was called equilibrium because that's the position where the force from the spring and the force from gravity balance each other out. So there's the same force up as there is down. That means there's a net force of 0, which means acceleration of 0 at that point as well. Now we can extrapolate for the points that are in between here. So if we have our maximum displacement upward here, our 0 displacement here, then any time in between there we're going to have some upward displacement. Between here we're going to have a downward displacement, and so on. You can do that with velocities and accelerations as well. I think it's worth noting here that whenever we have a maximum upward position, we also have a maximum downward acceleration. So those two are just flip-flopped from each other. And whenever we have a maximum downward position, we have a max upward acceleration. It's also worth noting that whenever our position or acceleration are at a maximum for either upward or downward, velocity has a value of 0 at those points. And I said we were going to come back to velocity and verify that, yeah, it must be a maximum at this point at equilibrium and a maximum downward at this equilibrium point. We can do that, or we can understand that by looking at the acceleration. So at this point right here, for example, our block or our tub has 0 velocity, and it has a downward acceleration. It's accelerating toward equilibrium. That's always true. This tub is always accelerating toward equilibrium. If it's at equilibrium, it's not accelerating at all. And the farther away it gets from equilibrium, the more, or the larger the value of acceleration toward equilibrium it has. And so at this point, it's accelerating downward. It's going to speed up, speed up, speed up, moving downward, right up until this point. Now at that point, acceleration is 0. So it's not speeding up and not slowing down at that point at all. It's picked up some speed, but it's not speeding up or slowing down anymore right there. As soon as it crosses past this equilibrium line, now our net force and our acceleration as a result both point upward, because both of those always point toward equilibrium. So as soon as our tub gets below equilibrium, our net force and our acceleration both point upward. So our tub is moving downward, but its acceleration is upward after it crosses this threshold. Whenever velocity and acceleration are in opposite directions, the object is slowing down. And so velocity and acceleration were in the same direction for this whole time period. And so it was speeding up, speeding up, speeding up right until this spot. Right after this, it starts to slow down. So this has to be the maximum value for speed. And it was moving downward, so the velocity is a maximum downward velocity at that point. Same deal here. It was at rest here. It starts moving upward, accelerating, speeding up, right up until it crosses the threshold. Now, once it's above the threshold, above the equilibrium position, acceleration is down. Velocity is up, acceleration is down. That's an object that is slowing down. So it reaches its maximum speed in the upward direction right there. Now that we've got a pretty clear understanding of the motion and the forces involved for the mass on a spring bouncing up and down, I want you to consider the other example I presented in class, which was the pendulum, which moves back and forth. So for Monday, what I'd like you to be thinking about is the same kind of analysis we did with the motion for this guy. So when would we have a maximum velocity in this direction, or a maximum velocity in this direction? When is velocity 0? When is displacement a max in this direction, or 0? And when is acceleration a maximum value in this direction, when is it 0? So those three quantities, position, velocity, and acceleration, I want you to do some analysis, to put some thought into the values and how they relate to a simple pendulum. Now, I'd also like you to think about one more thing, and that is, what is the restoring force in this situation? So we always have to have a force that points back toward the equilibrium position. So I want you to be thinking about, in this situation, for the pendulum that goes back and forth, I told you this is simple harmonic motion, so that must mean that there's some force that points back toward the middle, back toward this position where it's hanging straight down. So what force is it that does that? And that force should be proportional to the distance that we pull it away from equilibrium. Is it? Does this really match the criteria for simple harmonic motion? Thanks a lot, folks. We'll see you at our next class. I look forward to working with you. Appreciate the time you're taking in.